Solutions have at least two parts, a solute and a solvent. And sometimes we need a quantitative measure of the concentration. You know, how much solute is in this solution. So one, one quantitation is mass percent. And there are several different ways of quantifying the concentration of a solution because the different ones are useful in different fields. So mass percent is one that's used quite a bit in medicine and biology. Mass percent follows the same pattern of a percent. So percent means per 100. So one way to think of mass percent, it's the number of grams of solute per 100 grams of solution. How many grams per 100 grams? So a solution with a concentration of 14% would be 14 grams of solute per 100 grams of solution. So if you want a mathematical equation for that, it's the mass of the solute divided by the mass of the solution. Now they sometimes get a little tricky on questions, and they'll give you the mass of the solvent and the mass of the solute and make you add them together. It's the mass of the whole solution. So that's the part, the solute, divided by the whole thing times 100. So the denominator is the solution, not the solvent. Mass percent is useful because it's very easy to make, say, a 0.9% sodium chloride solution. 0.9% means 0.9 grams in 100 grams. So you weigh out 0.9 grams of sodium chloride, you add water till the whole thing is 100 grams, and there you go. You don't have to do a lot of thinking about moles and other things like that. So let's do, I don't know how many examples are coming up. Let's do the first one and see what happens after that. Calculate the mass percent of a sucrose solution containing 11.3 grams of sucrose and 412.1 milliliters of water. It says assume that the density of water is 1 gram per milliliter. Well, if the density is 1, come on, drawing mode. There we go. Pick a good color. If the density is 1, then how much does 412.1 milliliters weigh? It's the same, right? Because there's 1 gram per milliliter, so we can prove it to ourselves like that. So the mass of the solvent, the water, is 412.1 grams. We're asked for mass percent. So that's the grams of solute divided by the grams of solution times 100. What's the mass of the solute? 11.3 grams. What's the mass of the solution? Well, 412 is the mass of the solvent. We need to add these two together, right? Because in that solution we have the water and the sugar. So we add them together. That's the mass of the whole solution. These units of grams cancel out. We're multiplying by 100. And we end up with a unit of percent. 11.3 divided by 423.4 times 100. The smallest number of sig figs here is in the 11.3, 3 sig figs, so I'm going to give my answer to 3 sig figs, 2.67. Any questions? You can't have a negative percent. You can't have a percent concentration that's greater than 100. We talked about sometimes we end up with a percent yield that's over 100 because of contamination or something that went wrong. In a mass percent, think about salt in water. Can the mass of the salt be more than the mass of the salt and the water? No. If it was 100% salt, then it would be salt and no water, which isn't even a solution. So if you ever come up with something that's greater than 100 for a mass percent, it's wrong. Okay? Sometimes percentages can be small. I sometimes see students do something like this, and they come up with this number, and then they multiply it by 100 again. Or they divide by 100. Don't do anything like that. You take the ratio of the solute to the whole solution, you multiply by 100, and you just write down what it says. Okay, don't pull anything fancy afterwards. There are other commonly used units. If you ever look at that document that the water company or the city sends you every year about your water quality and safety and stuff, you'll see some of these units. ppm, ppb. Okay, parts per 100 is the same as percent. Parts per 100. ppm stands for parts per million. ppm. That is the number of grams per million grams of solution. Same idea, but this is good for measuring a much smaller concentration. You can also have parts per billion, which is the number of grams of solute per 1 billion grams of solution. Okay, so how would you calculate parts per billion? Well, same pattern for percent, which is parts per 100. So parts per billion would equal the grams of solute divided by the grams of solution. That's a common chemist abbreviation for solution. In a percent, we multiply by what? 100, because it's parts per 100. For parts per billion, we'll multiply by a billion. Okay, so a million is 10 to the 6, a billion is 10 to the 9. So if something is parts per billion, it's a very, very low concentration. Why do we have all these units? Well, why do we have meters and kilometers and micrometers? Because we like to have a unit that is similar in size to what we're measuring, so that we don't end up with crazy big and small numbers all the time. We don't want to list our concentration as 1 times 10 to the minus 14%. It's hard to keep track of. And so if all the concentrations are in that range, we're going to end up with, you're going to use something like 1,000 parts per million. Billion, I mean. And so you tailor the unit to the size of the thing that you're measuring. That's why we have all these different units. So these at least are all related to each other, and what's different is what you multiply them by. So we need to know how to calculate mass percentages, but we also need to know how to use them as a conversion factor. Remember that mass percent is equal to mass, or grams per 100 grams. When we're calculating the mass percent, it's generally easier to take what I did before, let's just back up there real quick, to do it this way. The mass of the solute divided by the mass of the solution times 100. When we're using it as a conversion factor, it's more convenient to think of it this way. Grams of solute per 100 grams of solution. So let's do an example of this. How much sucrose in grams is contained in 355 milliliters, which is a 12-ounce can, of a soft drink containing 11.5% sucrose? And we're told to assume a density of 1.04 grams per milliliter. Okay, so let's just write down these numbers. We've got 355 milliliters, and we've got 11.5%, and we've got 1.04 grams per milliliter. And what are they asking us for? How much sucrose in grams? So we're looking for grams of sucrose. So we're trying to find grams of sucrose. This is a volume, and here we're told the density. Is this the volume of the solvent, or the solute, or the solution? It's the solution. It's the can of soda. So this is the volume of the solution. I don't want to do that. So that's milliliters of solution. What does this percent tell us? This tells us 11.5 grams of solute per what? Per 100 grams of solution. Because that's what percent means, per 100. So 11.5% means 11.5 grams of the solute per 100 grams of solution. Do we know how many grams of solution we have? What did they give us? They gave us a volume. But they also gave us the density. Could we calculate the mass?
Yes.
Yeah, we can. This is Mrs. K not planning ahead. There's been a lot of that lately. So it's kind of tipping up as we go along. That's supposed to be a sign of optimism. So milliliters cancel milliliters. 355 times 1.04. This tells us that the mass of the whole solution is 369.2 grams. That's the mass of solution. How many sig figs does that number have? Should it have? 3. 355 and 1.04 both have 3 sig figs. So I'm going to underline the 9 here. I'm going to let the 2 hang around, but I want to remind myself that that number only has 3 sig figs. So now I've got the mass of the solution, and I've got this relationship. The sucrose is the solute, right? It's what's dissolved in the solution. So how do we get the grams of sucrose? We subtract. No subtracting here. So let's look at these numbers. What do we have here? This guy down here, we already used him, right? So I'm just going to kind of cross him off, because generally you only use numbers once. And so what numbers do we have left? We've got this one over here, and we've got this one over here. I'm assuming that we're confused, about what we're supposed to do here. Well, let's look at this. Probably we're going to have to combine these two somehow, right? Dimensional analysis should always be your first thing you think of. Can I use dimensional analysis? Can I look at the units and figure out what to do? Yeah, we can. This looks like a conversion factor, doesn't it? Something per something else. That's a relationship between two things. So that means this is what we start with. Grams of solution. So 369.2 grams of solution. And let's remember what we're trying to find, the grams of solute. I just realized that red pointer is not so good. I had changed it to match a different PowerPoint I was doing. Green shows up better on the screen. We're trying to find this. So here's our grams of solution, and in this one we've got solute and solution. So we're going to put the units in first. We're trying to find grams of solute. I want that on top. I want grams of solution on the bottom to cancel that guy out. Then we look at our concentration here, 11.5 grams of solute, so that goes on top. and 100 grams of solution will go on the bottom. So we've got 369.2 times 11.5 divided by 100. This number should have 3 sig figs, so I'm going to go ahead and round it off here. 42.5 grams. That number should not be larger than the mass of the solution, right? The whole can of soda, the soda in it, weighs 369 grams. If I came up with a mass of sugar in there that was 500 grams, we would know that that's impossible, right? This number is smaller, and so that suggests that we probably did it correctly. This is not the only way to solve a problem like this. Some of you have a great understanding of percentages, and you have other ways of doing percent problems. You go right ahead. Okay? You can also do this with algebra and write out the percent equals grams over grams times 100 and rearrange and solve things that way, and that's fine too. But this approach using dimensional analysis and treating this percentage as a conversion factor, I think is the most straightforward way for someone who doesn't have a different way of doing it. Any questions?